Welcome to topic 9.5. This is our last topic for Unit 9, looking at the introduction to mole conversions. For this unit, or for this topic, I should say, this is where we're going to learn how to determine an empirical and molecular formula of a compound. Essentially, how do we know what a compound is made up of based on data we can obtain through the lab. So you do need your calculator and you need your periodic table because we are going to be needing molar masses from it. So as a chemist, we can describe formulas as either being the empirical or molecular formula. The molecular formula is oftentimes called the true formula, and the empirical is the lowest whole number ratio of atoms to that. So for example, I have an example here of glucose. So glucose has a backbone of carbon, hydrogen, and oxygen. So this is the true formula of glucose, so the sugar that you encounter in your everyday life. And so this shows us what we have actually in the formula. It's made up of 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. The empirical formula gives us the ratio of these atoms, and it always has to be a whole number. We can't have partial atoms, so we can reduce this down to a 1:2 to 1 ratio. So for every 2 hydrogen, we have 1 carbon and 1 oxygen. So we're going to start first by calculating what's called the empirical formula. Then we use that to determine the molecular formula. So before we get into the actual calculations, I just want you to understand what the difference is between the two and determining if these formulas are an empirical or molecular formula. So when you look at this, we have CH6, you have to determine if it can be simplified or not. Well, 6, yeah, it can be reduced, but 1 can't, and we can't simplify those down and keep whole numbers. So this is the lowest ratio we can have. For every 1 carbon, there's 6 hydrogen, so this is definitely an empirical formula. For letter B, it's a 2:2 ratio, and again, you can simplify both of them, so it's a 1:1 ratio, so that is a molecular formula. In letter C, we have 12 carbon for every 6 hydrogen, so we can simplify that down and keep a 2:1 ratio, so that is going to also be a molecular formula. Now here in letter D, we have a 2:4 ratio, and you're thinking, yeah, I can simplify that. But you have to be able to simplify all subscripts, and so we only have 1 oxygen. So it's a 2:4:1 ratio, and that cannot be reduced and keep whole number atoms. So this is also going to be considered an empirical formula. So there's a little rhyme that you can use to help kind of remember the process to finding an empirical formula. The first step is percent to mass, mass to mole, divide by small, multiply till whole. So I'm going to walk you through that. The next part of your notes, these are the 4 steps, meaning what do I mean by each part of that little rhyme of what is percent to mass, what step is mass to mole, what do I mean by divide by small, and what do I mean by multiply till whole. So I'm going to walk you through that in the actual examples. This is more for you when you're on your own if you need it. So this first example, we have what is the empirical formula of a compound that is 78.1% boron and 21.9% hydrogen. So the first portion of that rhyme, and let me grab that sheet of paper, said percent to mass. So that's the first thing we need to do is in laboratories, we have ways of analyzing composition of things. And so probably done with a spectrometer, we can determine that this compound, we know that A, it's made out of these 2 elements, and we know their percentages. So I'm going to start out with this first one. So we have 78.1% boron. Well, you can assume that if you had 100 grams of this compound, whatever it may be, 78.1 grams of that compound would be boron, because 78.1% is boron, if we use that assumption that's out of 100. So we can just say that instead of 78.1% boron, that's equivalent to having 78.1 grams of boron. We're going to do the same thing with our other component, which is the hydrogen. It says that we have 21.9% hydrogen. So what we really mean to say is we have 21.9 grams of hydrogen. And so that's the first step of the rhyme, percent to mass. The next step, it says mass to mole. And so we know how to convert mass to mole, and that is using the molar mass. So this is a 1-step conversion that is going to rely on your periodic table. And so again, if you look at the mole map, if you're not sure where you're at, you again are using molar mass to complete the conversion here. When you look at your periodic table, And I'm going to pull my worked out problem near me. There we go. So we have 10.81 grams according to the periodic table. And so I'm going to go ahead and write in my answer. So with division, I got an answer of 7.22 moles of boron. Now in the next example, or the other element I should say, same idea, but we're going to substitute in hydrogen's mass of 1. So that one's easy. We get 21.9 moles of hydrogen. So that's mass to mole. The next line in the rhyme is divide by small. So essentially what we're doing is we need to find the ratio between these elements. So boron we have less of. We have 7.22 moles. So you divide by your lowest number of moles out of all the elements that make up the compound. In this case, it's just the 2. So what we do is we divide each of these by the lowest number to get this proportion. So when we do that, obviously this one's going to come out to 1. And so when you divide out the one with hydrogen, you get approximately 3.03. So what this is doing is this is telling us that for every 1 boron, there is 3.03 hydrogens, which what we're going to do here is this is close enough to 3. It has to be a whole number. We're going to say that this is 3. So this is a 1-to-3 ratio. So the very last step is to write your actual empirical formula. And so list them out in the order that the problem gives them to you. So boron is listed first. We have 1 of them. We don't write a subscript 1. The next element is hydrogen, and we said it's 3. So this here is the actual empirical formula. We determined it's a 1-to-3 ratio based on the percent composition of these 2 elements in the compound. Now, the last line of the rhyme is multiply till whole. Well, they came out to whole numbers, so that line does not apply to this example. In our next example, that last line is going to apply. So it asks, what is the empirical formula of a 10.15 gram sample of a compound that contains only phosphorus and oxygen? It has a phosphorus content of 4.433 grams. So in this particular example, they started out by giving us the mass directly. So problems with empirical either start with percentages like the last example, or they start with grams. It doesn't matter. You just assume the unit is grams. So the first thing we can work with is this 4.433 grams of phosphorus. So after percent to mass, which we have mass, it's mass to mole. So we use molar mass. So 1 mole is 30.97 grams. And we get an answer of 0.1431 moles of phosphorus. Okay. The thing with this sample is it tells us nothing about the oxygen directly. However, it tells us the sample has this much mass. Of that, it's made up of 4.433 grams of phosphorus. So that means the remaining piece is all oxygen. So that's a really easy thing to figure out. We just need subtraction. So we're going to take that 10.150 grams and get rid of the mass contributed by the phosphorus. And that gives us 5.717 of oxygen. Now, the one thing that's weird about this, and that's a hard habit to get out of, is we think of oxygen as being Hoffman-Kleiber, which it is. However, when we're working through empirical formulas, we're not talking about just oxygen on its own. It's in a compound, so it's just O. So we don't have Hoffman-Kleibers in here because, again, they are in compounds. So when it comes to the molar mass here, it's going to be 16, not 32. So we're dividing it out with that 16, and we get 0.3573 moles of oxygen. Okay, so now the next thing is divide by small. So which one is our lowest contributing mass or number of moles? And that's definitely the phosphorus. So we're going to divide them out to get our ratio. So this again will always be 1. And we have 1431. So when we divide this out with the oxygen, the thing that's a little bit different is we get an answer of 2.497. Now, in the last one, we had an answer of 3.03, which was close enough to saying 3. However, we're basically at 2.5. So this is where the last line of the rhyme rhyme comes into play, multiply till whole. So from here, what you need to do is, because 2.5, it's not close enough to 2 and it's not close enough to 3, we need to multiply to get our ratio. So we're going to take this times 2. We're going to take this times 2. What you do to one element, you do to the other, kind of like when you rearrange to solve for x. And so the reason in why I did this is if I take 2.5 times 2, that gives me a whole number of 5. This gives me 2. So this is a 2 to 5 ratio, not a 1 to 2.5 ratio, because we, again, cannot have half oxygen atoms. So those become our subscripts. So our empirical formula is going to be P2O5. And that's your final answer for this example. There are other scenarios where you can get like a third or 2/3. I don't show you those. I don't work with those at this level. The only time you need to do this multiply till whole is when you get a half. Everything else is going to round directly up or down. It'll be very close to the corresponding number. If you want to take a moment and pause the video and work this one out, see how you're doing with this concept, and I will show you how to work the problem out, but I would recommend pausing it for a moment. Okay, so hopefully you took my advice, and so what you should have done is basically we swap out this with grams. So you have 3 elements to work with in this scenario. You should have started with the 74.0 grams of carbon divided by 12.01, and you get 6.161 moles of carbon. In the hydrogen, you have 8.65 grams of hydrogen. Because of its molar mass, you get 8.65 moles of hydrogen. And then here you have the 17.3 grams of nitrogen. 14.01 is the mass. And so when you divide that out, you get 1.234 moles of nitrogen. Again, we now need to get our ratio. You do that by dividing by small, which is the nitrogen. So divide these all by 1.234. So it looks like for the hydrogen, I got approximately 7.009, aka 7. And then let's see here. So 1.234. And carbon, it looks like I got 4.993. So basically 5. So for your empirical formula, it should be C5H7 with just 1 nitrogen. And that's your final answer. Okay, so molecular formula isn't too much of a branch off of what we just did. So molecular formula gets us the true ratio, the true proportion of the carbon, hydrogen to nitrogen, for example, in the last example. So you need to know your empirical formula. So some of these you have to find the empirical formula before you can even start this process. And what you need to start with is you need to know the molar mass of that empirical formula, the lowest ratio. So in a lab, we can get the molecular mass. We can figure out what is the molecular mass of the true formula of this compound. And then we find the ratio, and that can give us the true subscripts. And so I'll show you what I mean by that. So here in example 1, it says a compound has an empirical formula of C4H4O. So basically they just did what we worked through. They were kind enough and gave it to us in this example. And it says it has a molar mass of 136. So the true mass has a mass of 136 based on this proportion of the 4 to 4 to 1. So we want to know what are the actual subscripts, what's the true ratio, or the true, not ratio, but the, again, true subscripts of the true number of atoms in that formula. So the first step is you need to know the molar mass of this. So where you have the C4H4O. So you always start with finding molar mass of the empirical. So we have 4 carbons at 12.01. We have 4 hydrogens at 1. And we have 1 oxygen at 16. So for my molar mass, I calculated the molar mass to be 68.04. Okay, so what we now need to do is we need to figure out the relationship or ratio between the true mass of the compound versus the molar mass of the lowest ratio. So all you do, and this mass of the true compound must always be given to you. You will never have to calculate that. So you take that 136 divided by the lowest ratio molar mass, so that's 68.04. What that gives you is 1.999, which we can say is 2. So what that means is the lowest ratio, this 4 to 1, based on the true molar mass, the ratio, the relationship is 2 times greater. So what you do is you then take this times your empirical formula. And this will give us the true subscripts to give us a molar mass of 136. So that gives us C8H8O2. And this is my molecular formula. This is the actual number of carbon, hydrogen, oxygen atoms. This was the lowest ratio. We find the relationship between these two and then multiply that difference to our subscripts, and that again comes out close to 136. So in this next one, it's kind of a double whammy in that it does not give you the empirical formula. So what you have to do is, just like the front side, you need an empirical formula. It just tells us how much we have of each, unlike the last one saying we have this empirical formula. So sometimes you have to complete both steps. So it's made out of hydrogen and oxygen. So we start with our hydrogen, and the first step is mass to mole. And we get 0.44 moles of hydrogen. Same thing with the oxygen. So we divide that out, and I got, looks like, there we go, 0.433. Or, yeah, 433. Divide by small. And we basically get a 1-to-1 ratio. So the empirical formula, the lowest relationship between these, is that it's for every 1 hydrogen, there's 1 oxygen. This is the empirical formula. So just like last problem, we're basically picking up with where we left off with what we did in example 1. We then need the molar mass of this compound. So we take 1 plus 12. Or no, not 12. We're not working with carbon, 16. So the molar mass of this empirical formula is 17 grams per mole. So the lowest relationship, that's the lowest mass. The true mass of the true formula, the molecular formula, is 34. So we take the true mass divided by the empirical formula's mass to get the true relationship between these two, which we get approximately 2. So that is our multiplier that we then multiply our empirical formula to get our true subscripts. And we get H2O2, which is hydrogen peroxide. And that is the molecular formula. Here's the last independent practice problem. If you want to pause the video and see if you can work it out, that is highly encouraged. So here we have 3 elements, and I have to buzz through this because I have a Google Meet to meet with you guys. So we have 3.33 moles of carbon. And I'm going to just go ahead and fill this out because it's the lowest. I'm going to go ahead and show that work so I'm not backtracking. The thing here says it rest as hydrogen. So what I did to get the 6.7 grams of hydrogen is that we know that a percentage adds up to 100. So I subtracted those other 2 percentages from 100, and that's where I got 6.7 grams from. So I divided by my small, so you get 1 carbon to 1 oxygen to 2 hydrogen. So then that's the empirical formula of COH2. You need the molar mass of this then, so add 1 carbon, 1 oxygen, and 2 hydrogen. You get 30.01. So from there, we divide it by the true molecular mass, which again is always provided by the problem. So you take 360 over 30.01, and you get approximately 12. That is our multiplier. That's the relationship between the lowest ratio to the true formula. So then you multiply that out to the COH2, and you get a molecular formula of C12O12H22. That's it. And now I'm going to go join your Google Meet.